Number one. So an electric field is an area around a charge where an electric force could, keyword is could, be felt. Okay, key word here is could. Doesn't mean you will have a force, just could find a force. Now, here's why that is. An electric field exists, what's called independent of charge, which means it does not matter what the second charge is. See, when we did force, we had charge A and charge B, and they repelled each other or they attracted each other. But they did something to each other. An electric field is an area around a charge where there could be a force, but you don't know what it is because there's no second charge. And so because there's no second charge, you can't figure out what it would be. You just know what it could be. We do this with gravity, right? It doesn't matter how heavy I am. I can figure out how strong is gravity here in Indiana. Or I can figure out how strong is gravity in Denver. So it doesn't matter how heavy I am. It matters about the mass of the Earth and what gravity is. Okay, I can figure out, if I don't worry about what the second charge is, I can figure out what's going on. Okay, the equation is E equals K, same K as before, 9 times 10 to the 9th, Q over D squared. You might be saying to yourself, Mr. B, isn't that the same equation we just did for electric forces, except instead of 2 charges, it's only 1? Yeah, it is. Now, D is the distance from a charge to some position. So, it's how far I'm looking for it at X. Here, let's do it X so you can see it better. So D is how far away X would be. And the unit is newtons per coulomb. So how is this different from electric force? It's finding the area a charge affects instead of the other charge it affects. Yeah.
So you know, like the iPhone things that have the charger on the back.
Yeah.
With that.
It's the same idea. The ones that you just like place on a mat. Yeah, it's the same idea. It's using an electric field to charge it.
Wait, so if I just like hovered my phone over it while it was on, it would just charge?
you need a specific frequency. It doesn't just work on anything. It might charge it like very, very, very slightly. But let me write down the light bulb demo one, and then I'll give you another example of that. It'll be a story time. Okay, light bulb demo. So light bulb lights up without being plugged in because it is in a field. Because it is in an electric field. Different today. All right, number 4. What is special about the electric field inside a conductor? So the electric field inside a conductor is 0. I should say it is 0. So if here's a conductor, all the electrons go hang out on the outside edge. What happens is the electric field that they produce is going to be is going to repel. Basically, it's going to repel each other. So it's going to create an electric field. Electrons, the electric field comes towards them. Okay? But if they're all on the outside edge and it's always coming towards them, it's going to pull the inside towards it equally, which is going to make it 0. So how does electric shielding work? Anything inside a conductor is safe from electric fields. But, all right, last one example problem. What is the electric field? 0.3 meters away from a charge of positive 6 times 10 to the negative 6 coulombs. Okay. So, first things first, draw a diagram. All you got to do for a diagram for this is draw a charge and draw the direction of the field. Okay, positive charges make fields away. Negative charges make fields towards. So, this is a positive charge, so it creates a field away from it. And it wants to know what the electric field is 0.03 meters away. Notice that it does not matter where I put the 0.03 as long as I have the distance listed. .03 here, .03 here, .03 here. It doesn't matter where the .03 is. It just needs to be in the problem. Okay? Okay, so the equation is E equals KQ over D squared. So E equals K, which is still 9 times 10 to the 9th. Q, which is 6 times 10 to the negative 6. Do not plug in negative signs if they're there, just in the powers. divided by the distance squared, 0.03 squared. Okay, so let's plug the numbers in and solve. 9 times 10 to the 9th times 6 times 10 to the negative 6 divided by 0.03 squared. And we get 6 times 10 to the 1, 2, 3, 4, 5, 6, 7th power. And the unit is newtons per coulomb. There you go. So, what happens if we tripled the distance? Well, if we made this distance 0.09 instead of 0.03, we would be further away. And so notice that as we get further away, the field spreads out. So if I move from a distance of 0.03 to a distance of 0.09, the field is going to be spread out more. So it should be smaller. So how much smaller? Well, it would be that much smaller squared. So if it's 3 times the distance, it should be 9 times less. If I made the distance 3 times closer, it would be 3 squared closer, so it would be 9 times larger. And what if we added more charges? Okay, if we added more charges, you would find the field of each charge and add.